Welcome. On this video, we're going to be discussing partial fraction decomposition. So let's get started. So what is partial fraction decomposition? Well, a rational expression can often be written as the sum of two or more simpler rational expressions. And the simpler rational expressions are called the partial fraction decomposition of a rational expression. In other words, partial fraction decomposition, it is a technique that we have to rewrite rational expressions. So how do we perform partial fraction decomposition? Well, let's take a look at example 1. It states, let's rewrite the following expressions using partial fraction decomposition. And right here on the right hand side are the checklists or the steps that we'll be taking to perform partial fraction decomposition. So let's get started. The first thing that we want to do, we want to factor the denominator. So let's take a look at the denominator, x squared minus x minus 6, and see if we can factor it out. Well, in this case, we can definitely factor it out. And we can factor it out as x minus 3 and x plus 2. So step number 1 is done. We already factored the denominators. What we want to do is identify the multiplicity of the factors. Notice that the factor x minus 3 has an exponent of 1. Therefore, it has a multiplicity of 1. X plus 2 has an exponent of 1, therefore it has a multiplicity of 1. Since they both have multiplicity of 1, we don't have to modify the setup that we're going to be performing in a couple seconds. The second example on this lesson is going to deal whenever we have multiplicity greater than 1. So step number 2, right now we're just going to skip it. For step number 3, which is what I call the setup. The setup, it says write constant numerators for each linear factor of the denominator. So what do we mean by that? Well, we're going to be taking the original expression and we want to write it in terms of the sum of the factors that we got originally. And what exactly are we going to put on the numerators? Well, on the numerators, we're just going to write some constants. I'm going to let a to represent the constant that will go on my first numerator, and I'm going to let b be the constant that will represent the numerator on the second rational expression. And this is the setup. This is actually what we want to do. We are given a rational expression, and we want to write it as the sum of two simple rational expressions. And the only thing that are missing is the constant of the numerator of the first and the constant of the numerator of the second. If we can properly find out what those values are, we have performed partial fraction decomposition. And that's actually the objective. We want to come up with values of a and b that will make this whole statement a true statement. So how do we accomplish that? Well, let's take a look at step number 4. So now that we have the setup, we want to multiply the equation by the LCD. So what is the LCD? Most of the time, the LCD is just going to be the denominator of the original rational expression, which in this case, the LCD is just x minus 3 times x plus 2. And let's just multiply the LCD to the left and the right. So if we multiply the LCD, we're going to get x minus 3 times x plus 2. And notice that that's multiplying the whole left-hand side. And we're going to do the same for the right-hand side. We're going to multiply by x minus 3 times x plus 2. By doing this, notice that the denominator is going to cancel out with the multiplication, since the multiplication is done on the numerator. So now on the left-hand side, we're just going to get x plus 7. Now on the right-hand side, we want to distribute this whole expression, x minus 3 and x plus 2. So if we distribute to the first term, notice that this x minus 3 is going to cancel out with this x minus 3. So what's going to be left is just a times x plus 2. Plus, let's distribute to the second term. And if we distribute to the second term, this x plus 2 on the denominator is going to cancel out with this x plus 2 on the numerator. So what's going to be left is just b times x minus 3. And why are we doing this? Because now notice that we went from rational expressions to not a single rational expression. We don't have to deal with denominators anymore. So what do we do once we have this? Well, let's just expand this. So let me just distribute the A. So I'm going to get AX. Let me distribute the A. So now we're going to get 2A. Let me distribute the B. So now we're going to get BX. And let me distribute the B. No, we're going to get negative 3B. And we're going to stop here for a second because let's just remember what we want to do. Originally, we wanted to come up with values of A and B that will make this a true statement. So we're essentially going to try to do the same here. We want to find out values for A's and B such that if I plug them in, it is equivalent to X plus 7. So how are we going to accomplish that? Well, let's think about this for a second. Let's say I have an expression that is 2x squared plus 3x plus 5. And I ask you, what values can I place here? What values can I place in these two empty slots that will make the left be equals to the right? And you might be saying, well, that's just pretty trivial. I mean, if I plug in on my first step, my first empty slot, if I plug in 2, then definitely 2x squared is equal to 2x squared. And if I plug in 3 here, then definitely 3x is equivalent to 3x. So therefore, if I plug in 2 and 3, then the left is equal to the right. Well, that's the same idea that we're going to be performing here. I'm going to be grouping the right-hand side in terms of its variables, and I'm going to match it with what's on the other side. So let's do that. On the right-hand side, let me just group those terms that have an x on them, which in this case, there are 2 terms. I have ax and I have bx. So if I group them and I kind of like take out an x as a factor, then I'm going to have a plus b x. I just factor out the x. Plus, notice that I still have these 2 terms. They don't have an x on them, therefore I can just treat them like if they were a constant. So 2a minus 3b. So why are we doing this? Because now I can just think about this. I want to come up with values of a and b that make the left equals the right. So we're essentially doing the same problem. So now if we come back to what we have here, what is the coefficient of x on the left-hand side? Well, the coefficient of x on the left-hand side is 1. So therefore, whatever a plus b is, it should be equivalent to 1, just like we just did here. The coefficients need to match in order for the whole expression to be equivalent. And that's essentially what I'm going to be writing now. I don't know what a and b are, but I know one thing. I know that if I add them up, it must be equivalent to 1, because that is the coefficient that is in front of x. And this is the coefficient in front of x on the right-hand side. And the same idea for what is left here. I know that if whatever constants I have, they must be equivalent to 7. And this is the expression for those constants. So therefore, I know that 2a minus 3b, that should be equivalent to 7. And what I have set up here, it's a system of equation. And now this system of equation, it is something that we can solve for because there are 2 variables and there are 2 equations, therefore it is solvable. So let's just solve this system of equations to find out the values of a and b. And now this becomes an Algebra 1 problem. So you can use whatever techniques you learn in Algebra 1 to solve for this system of equations. What I'm going to do here, I'm just going to multiply -3 to both sides, and then I'm going to add them up in order for the b to cancel out. So if I do that, I'm going to get -3a minus 3b equals -3. I get 2a minus 3b equals to 7. Just notice that I should have multiplied by +3. Sorry, so let's multiply by +3. So therefore, this is +3. This is +3b. And now this is just +3. So once I have that, let me just add both equations. By doing that, I have 5a. Now the b's are going to cancel. 3b minus 3b, they cancel out. And 7 plus 3, so that's equivalent to just 10. To solve for a, let me divide it by 5. So now I have an expression that a has a value of 2. And that's good. We're halfway there. So now what we want to do, we want to find the value of b. But since I already know that a is 2, and I know that this equation, it is true, but let me just plug in this a to my first line on my system of equation to solve for b. So now I'm going to get the equation a plus b equals 1. If I plug in a to be 2, I'm just going to have 2 plus b equals 1. And now I know that b has a value of -1. And we're done. We know what the value of a is, and we know what the value of b is. So if we go back to our setup that we had initially, well, let me just rewrite the setup here. Remember that our setup was that x plus 7 divided by x squared minus x minus 6. We said that that was equivalent to some a divided by x minus 3 and some b divided by x plus 2. Remember that this is the setup. This is the setup that we had here. But we already know what a is, and we already know what b is, so let's just plug that in. A has a value of 2. So let me just erase this 2. Let me just erase that a. And let me just substitute it with the 2. And the same goes for b. Let me erase the b, since I already know what the value is. So now that becomes -1. And now this is our objective. Notice what we have done. We were given this rational expression, and what we have done is we just rewrote that original rational expression into a sum of two simpler rationals expressions. And we call it simpler rational expressions because notice that the denominator is just a simple binomial, x minus 3 and x plus 2. So let me actually just rewrite this. Instead of saying plus -1, that just looks weird. So let me just say it's just minus here. And we're done. This is how we can perform partial fraction decomposition. Let's just go over the setup. So remember that the first step that we did here, we factor out the denominator of the original. Once it's factored out, I perform the setup. I say, well, the original should be equivalent to a over the first factor plus b over the second factor. And now that we have the setup, we multiply by the LCD. So we multiply, and then we regroup here in terms of its variables. Then we set the coefficients of each of those variables equal to each other. We had a system of equation, and we solved the system of equation to solve for a and b. And at the end, we just want to come back to our setup and just plug in the values that we found algebraically. So this was our objective. We have performed partial fraction decomposition. So let's take a look at another example that is a little more challenging. And you can see that it's a little more challenging just by the way that it's already written here. But still, it is essentially the same idea, but you will notice that this problem, it's a little bit different. So the strategy, it is still the same. Let me take a look at my denominator and let me see if I can factor it out. Now you can just verify this on your own time, but the denominator can be factored out as 5. So the numerator is 5x squared plus 20x plus 6. And now the denominator can be factored out as x times x plus 1 to the second. You can verify. You take out an x from here, and now you're going to end up with x plus 1 to the second. So therefore, my denominator can be just rewritten in this form. And the first thing that you might notice is this. Notice that x has a multiplicity of 1, and x plus 1 has a multiplicity of 2. So when we perform our setup is going to be a little bit different. Because now notice that my LCD, it is x times x plus 1 to the second. So we're going to have one denominator for x. We're going to have one denominator for x plus 1. And we're going to have another denominator for x plus 1 all to the second. So this is the difference. If you have a multiplicity of 2, you have to write down that binomial as many times as the multiplicity that you have. So let's assume that we had a multiplicity of 4. Then we would have one denominator for x plus 1, one for x plus 1 to the second, one for x plus 1 to the third, and one for x plus 1 to the fourth. So the multiplicity, it is a little bit tricky because you want to take in consideration all possible multiples that come from that multiplicity. So this is the setup, since we do have a multiplicity of 2. Now that we have that, let's just set it up. I don't know what that constant is. I'm going to call it A, I'm going to call it B, and I'm going to call it C. And the procedure, it is essentially the same as we did previously. Let's multiply the left and the right by the LCD. So let's multiply this of x times x plus 1 to the second. And let's multiply the right hand side of x times x plus 1 to the second. By doing that, notice that this is going to cancel out with this denominator. So what I'm going to have left is 5x squared plus 20x plus 6 equals, and again, remember that we're multiplying this whole expression. So if we do that, if we multiply it to the first term, this x is going to cancel out with this x. So what's going to be remaining is a times x plus 1 to the second. If I distribute this the second term, notice that this x plus 1 is going to cancel out with 1 of this x plus 1 to the second. So what we're going to have left is b times x plus 1. And lastly, if we distribute to the third term, we're going to have this x plus 1 to the second is going to cancel out with this x plus 1 to the second. So therefore, we're just going to have c times x. So let's just expand this, just like we did previously. 20x plus 6. So now we're going to have a times, well, x plus 1 to the second, that's x squared plus 2x plus 1, plus b times x squared plus x plus c times x. All right, so let's just distribute one more time. Let's try to fully simplify or fully expand. So if I distribute, I get a x squared, and if I distribute, I get 2ax, and if I distribute, I get an a. Distribute, I get bx squared. Distribute, I get bx. And lastly, I just get cx. So even though you have a lot of terms on the right-hand side, we're still performing the same idea as the previous example. Now that it's fully simplified or fully expanded, let me try to just regroup in terms of its variables. So let me take a look at those that have an x squared on it. So I have a x squared and b x squared. So if I group them and I factor on x squared, I'm going to have a plus b x squared. Let me take a look at those that have an a on them. So I have 2ax, bx, and cx. So if I just group them and I factor in x, I'm going to have 2a plus b plus c times x. And the variable that is just remaining there, it is just a. Notice that that's the only constant there. So I'm just going to write it as plus a. So the same idea. Now that everything is being grouped in terms of its variable, I'm just going to say, well, let me just make the constants equal to each other. So on the left-hand side, in front of x squared, I had a 5. And on the right-hand side, in front of x squared, I have the expression a plus b. So therefore, if I want them to be equal to each other, I should set up a plus b to be equal to 5. On the left-hand side, I have a 20 in front of x. And on the right-hand side, I have this expression in front of x. So therefore, they must be equal to each other. So 2a plus b plus c, that is equivalent to 20. And lastly, I have 6 as a constant, and a is my only constant. So therefore, I have that a is equal to 6. So what we want to do now is, let's identify values for a, b, and c. But notice that we already have a value. A equals 6 for my system of equations here. That's what we got in the last line. So if I already know that a is equal to 6, notice that I can use the first line to solve for b. So now if I use the first line, so a plus b is equals to 5, and I plug in 6 for a, now I know that b is equivalent to -1. So the only thing that we're missing is the value of c. But where can we get c? Well, notice that in my second line, I already know the value of a, I already know the value of b, so if I plug it in, I can definitely solve for c. So let's just do that. So for the second line, a plus b plus c is equal to 20. So now if I plug in a for 6, and if I plug in b for -1, now I'm going to get 12 minus 1 plus c is equals to 20. So now this becomes 11 plus c is equals to 20. Take away 11, take away 11. So now I know that c is equivalent to 9. And we're pretty much done. Because now I know what a is, what b is, and what c is. So as our solution, let's just rewrite the setup that we had. The setup that we had was that a x squared plus 20x plus c all over x cubed plus 2x squared plus x, that was equivalent to a over x plus b over x plus 1 plus c over x plus 1 to the second. But we already know what a, b, and c are, so all we gotta do is just plug them in. So a, let's substitute it with 6. b, let's substitute it with -1. And c, let's substitute it with 9. And we're done. This will be the partial fraction decomposition of the problem that was given to us originally. And again, this just looks weird. Plus, minus, -1. So I'm just going to say that this is just a minus in front of the whole fraction. So this is the idea. We were given a very complex rational expression. And what we have done, we have rewritten that same expression. But now notice that those rationals are way more simple than what is being given to us. And that's the idea behind partial fraction decomposition. And with this, we conclude our lesson for partial fraction decomposition.